So when we talk about mixtures, there are two varieties: homogeneous mixtures and heterogeneous mixtures. Now, a heterogeneous mixture is one where the composition varies from one region to another inside the mixture. That chicken noodle soup I was talking about. Whole blood is considered heterogeneous because under microscope you can see blood cells. Ocean water is heterogeneous. A chocolate chip cookie is heterogeneous. A pizza is heterogeneous. I'm always hungry, guys. Marble, granite are heterogeneous mixtures. Okay? A homogeneous mixture is one where the composition is consistent from one region to another inside the mixture. So heterogeneous is mixing of large objects. Homogeneous is mixing happening on that molecular level, that submicroscopic level. So a glass of tea without ice cubes in it should be homogeneous. Tap water should be homogeneous. If your tap water is chunky, don't drink it. Air should be homogeneous. Blood plasma is homogeneous. But those are some good examples. Your Kool-Aid should be homogeneous. If your Kool-Aid's chunky, worry about it. Okay? So heterogeneous, homogeneous. So I've identified the building blocks of chemistry as atoms, but the idea of the atom, really as we understand it today, is not that old. It dates back to the early 1800s. I think it was proposed in 1803. Okay? So let's talk about where the idea of the atom actually started. The atom was kind of resurrected from a Greek idea by the two Greek gentlemen there, who I will not butcher their names, but you can see their names, okay, who theorized that if you took a block of gold, a hunk of gold, and you cut it in half, and then you took the halves and cut it in half, and you took the halves and cut it in half, that there would have to be some point where if you cut it in half, you would no longer have gold. Now, this was opposed to the ideas of Plato and Aristotle, who thought that there were only really four things that stuff was made out of: ether, dirt, fire, and water. Well, air, dirt, fire, and water, cosmic ether. And you could combine, if you combined them in the right ratios, you could make anything, and they thought that, yeah, you could keep dividing gold in half for forever. Now, they were the big name guys of their day. They squashed the idea of atom, and it lay dormant until 1803. Ancient Greeks, 1803. It's a long time. Okay? So in the 16th century, the 1700s, we started to see an emphasis being put on experimentation and observation. Okay? Now, if we think about experimentation and observation, this is a big difference from the Greek approach. Aristotle and Plato thought that everything came from the mind of man. And if we thought it, that was the way it was, and we didn't need to observe the world around us. Not a real sciencey modern approach. Okay? And out of these experiments and observations, we're going to see a reemergence of the atom. So it all starts with three laws. Now, guys, a law is just a statement of fact. It doesn't say why it is this way. It just says this is the way it is. Laws are based on experiments, extensive back and forth between the budding scientists of the day until they came up with these ideas. Okay? The law of conservation of mass says matter is neither created or destroyed in a normal chemical reaction. Okay? Up until this point, they thought that stuff could poof into existence and poof out of existence. Because, you know, if you took a piece of paper and you burned it, and you weighed the ash after you got done burning it, it weighed less. So poof, part of it just disappeared. They didn't take into account that gases were being produced and escaped into the environment. So a guy by the name of Lavoisier took on doing some experiments in closed containers where he trapped everything. Nothing could come in or go out. And when he did these reactions in closed containers, what he saw was that the mass didn't change. That the chemical process takes one type of substance and converts it into 2 or more different types of substances, but that the actual mass didn't change, which means that matter was conserved. Okay? So you have as many atoms after a reaction as you do when you start a reaction. Okay, keep scrolling. Okay? Now you can look at the conceptual connection on page 42, 1.3. I do not have a working way to zoom in on a question, so I'm going to let you do that on your own. The answer to conceptual questions are at the end of the chapter, so you can look up the answer. Now, the law of definite proportion. It says all samples of a given compound, regardless of their source or how they were prepared, have to have the same proportions of their constituent elements. It says if I've got water, no matter if I got water out of my tap, your tap, pulled it out of the river, that if it's water, I've got to have the same ratio of hydrogen atoms to water atoms. To oxygen atoms. Now I am going to go through this problem with you. So I'm going to read it to you and we're going to look at it. It's on page 43, okay, in your textbook. Practice problem 1.1. Come on, practice problem 1.1. Might help if I get to the right point. Now, 43. Okay guys, I'm going to have to stop right there. I actually brought the wrong textbook down with me. So, no, let me talk about the law of multiple proportion, and then the next video I do, we'll start off by doing practice problem 1.1 and then the practice problem that goes with law of multiple proportion. So let me talk you through the law of multiple proportion, and then I'll go grab the right book and we'll do a couple of practice problems. Okay? The law of multiple proportion says when 2 elements A and B form 2 different compounds, the mass of the element B that combines with 1 gram of element A in each substance can be expressed as a ratio of small whole numbers. What does that mean? So if I look at the compound hydrogen peroxide and I look at the compound water, they combine just 2, both contain just 2 elements, hydrogen and oxygen. So if I look at the amount of oxygen that combines with 1 gram of water in, 1 gram of oxygen, one more time. If I look at the amount of oxygen that combines with 1 gram of hydrogen in water, and I look at the amount of oxygen that combines with 1 gram of hydrogen and hydrogen peroxide, those 2 amounts of oxygen are going to be related to each other by a small whole number ratio, like 1 to 2 or 3 to 4. But it'll be a nice small whole number ratio. Okay guys, that's where I'm going to stop. I'll pick up here next time. We'll do 2 example problems and then we'll talk Dalton's atomic theory. Okay guys, I am back and we're going to talk about the conceptual questions and for the law of conservation mass, law of definite proportion, and the law of constant composition. And the first problem we're going to look at is the law of conservation of mass problem. It says when a log completely burns in a campfire, the mass of the ash is less than the mass of the log. What happened to the matter that composed the log? Think about it for a sec. Okay? We know that part of it is in the ash, but it's much, much less. That's because the rest of it escaped into the atmosphere as carbon dioxide and water. Okay? It didn't disappear, it just went into a form that we didn't trap. Okay, so we're going to move on to the next question. And we are looking at the law of definite proportion. We're going to look at page 43 at problem 1.1. Okay? Okay, 43, 1.1. Now, let's read through it, and then we're going to do it. Now, we look at the problem. It says 2 samples of carbon monoxide decompose into their constituent elements. One sample produces 17.2 grams of oxygen. So I'm going to write that 17.2 grams of oxygen. And 12.9 grams of carbon. Our second sample produces 10.5 grams of oxygen and 7.88 grams of carbon. Now guys, I'm going to shift you over here so we're looking at the whiteboard. Okay? So there's our 2 samples, sample 1 and sample 2. Now I'm going to look at the ratio of oxygen to carbon in both situations. Let me grab a calculator. So if I take 17.2 grams of oxygen and divide it by 12.1 grams of carbon, 17.2 divided by 12.1, I get 17.2 divided by 12, that's 12.9. Why did I write 1? I get 1.33 grams of oxygen for every 1 gram of carbon. Okay? Now, if the 2 samples are of the same compound, I should get the same ratio. So if I take 10.5 grams of oxygen and divide it by 7.88 grams of carbon, 10.5 divided by 7.88, I get 1.33 grams of oxygen for 1 gram of carbon. These match. Since they match, I know they're the same compound. Okay? So that's the law of constant composition. Now, looking at our last practice problem, the one that deals with the law of multiple proportion, we're going to look at practice problem 1.2. Okay? Over a page. So let's look at this problem. Now, let's read it. If we read the problem, it says hydrogen and oxygen form both water and hydrogen peroxide. Okay? It says the decomposition of water gives us 1.25 grams of hydrogen for every 1 gram of oxygen. Sorry guys, I'm erasing the whiteboard so we'll have room to work. So our first one there, we are given 0.125 grams of hydrogen for every 1 gram of oxygen. Okay, and that's for water. The hydrogen peroxide tells us that we've got 0.0625 grams of hydrogen for every 1 gram of oxygen. Now, the law of multiple proportion says that when I compare the hydrogen for water, it combines with 1 gram of oxygen, to the hydrogen for hydrogen peroxide for 1 gram of water, I should get a whole number ratio. So if I take 0.125 hydrogen over 0.0625 hydrogen, then what I'm going to get is 0.125 divided by 0.0625. I get 2 grams of hydrogen for the water compared to 1 gram hydrogen for the hydrogen peroxide. So they're in a 2-to-1 ratio, okay? And that's a small whole number ratio. It could be 1-to-3 or 2-to-3, just as long as it's a small whole number ratio. But that's what the law of multiple proportion states. Okay guys, let's get back lined up on the screen. And let's move on. Okay, what we're up to now is Dalton's atomic theory. Now, Dalton's atomic theory is on page 45 in your textbook. I do not want you to have this sucker memorized, but I do want you to be really familiar with it because I will ask you questions about it. It's the foundation of modern chemistry. Now, Dalton came up with his original atomic theory in 1803, okay? So this has got a little bit of age on it. And we're going to look first at Dalton's original atomic theory, and then we're going to look at how it's been modified with time. Now, remember that a theory is a big overarching explanation of how a whole lot of things work. Theories can be thrown out, theories can be modified with time. Dalton's atomic theory is going to be modified with time, but a theory is a big document. It's a big idea. It's vetted with lots of experiments. A lot of people have looked at this and challenged it and poked it, and it's a big overarching explanation. And we use a theory until we find that something's wrong with it. If it can be modified a little bit, we modify and roll on. If it can't be modified and it's just dead in the water, we toss it out and we start over. But theories they carry a lot of weight because they've had a lot of experimentation and a lot of exploration that has gone with them. Okay, so let's look at the points of Dalton's atomic theory. Point 1, each element is composed of tiny indestructible particles called atoms. Dalton thought of atoms as the ultimate marble. Okay, they're super teeny, BB's gone mad. Okay, and he said that each one of them was indestructible. Anything I've highlighted in yellow is something that we're going to have to change later on. Okay, point 2. All atoms of the same element have the same mass and other properties that make them different from atoms of other elements. So an atom of hydrogen somehow fundamentally looks different than an atom of zinc, which looks fundamentally different than an atom of chlorine. Okay? atoms of different elements combine in simple whole number ratios to form compounds. Now, Dalton is building on those 3 laws that we just talked about. Okay? Atoms of one element cannot be changed into atoms of another element. Now, this was a biggie at his time because alchemy was running rampant in the late 1700s and the early 1800s. And alchemy is where they were trying to essentially turn things into gold. Okay, they used a lot of mercury and lead, and they did really weird metallurgical things trying to make gold. They didn't accomplish it because it can't be done. Okay, so atoms of one element cannot be changed into atoms of another element. Now notice I've highlighted the cannot be changed, because if we talk about nuclear chemistry, it throws a whole nother twist onto this. In a chemical reaction, though, atoms only change the way they are bonded together. And we're going to be dealing with benchtop chemistry, and we're going to do chemical reactions. And in a chemical reaction, we only rearrange how the particles are built together. You've knocked apart your Lego house, and you're building a Lego castle out of it now. Okay? Now, this was a really revolutionary idea when he proposed it, and it changed the whole science landscape. Dalton became the big man of science for the rest of his life, and you didn't want to cross him. And because of that, a few mistakes were made along the way, and they kind of were corrected after Dalton died. Okay? Now, in the late 1800s, a guy by the name of J.J. Thomson was working on the properties of a cathode ray. Now, let me pull out the cathode ray tube so I can show you what a cathode ray is. Things are always much more fun if we got toys. Okay, guys, let me set up the toy here. Toy should not be on. Okay, we gotta adjust this. Okay, guys, I've got the cathode ray. Now let me show you what a cathode ray looks like. Okay. I know we've got some dead time here, but it'll be worth it, I promise. There should be a big magnet in my desk drawer. It's a weird shape. Okay, guys, let's see if you can see the cathode ray here. Yeah, let's adjust this down a little bit. That, guys, is a cathode ray. Now, let's play with it just like J.J. Thomson played with it. Okay? J.J. Thomson wasn't having quite this sophisticated setup. He had a guy hand cranking to generate electricity, but he started playing with this by bringing magnets up. Okay, notice how the beam deflects as I bring the magnet up. Now, if I had some really nice, powerful magnets with a clear see how I get it to deflect up like that now? And I can get it to deflect down. Okay? This is what Thomson was doing. And by looking at how it responded to a magnet, okay? Looking at how the beam responded to the magnet. What Thomson was able to figure out was that that beam of particles was made up of negatively charged particles. And they were very, very tiny. He changed out the gas, he changed out the electrodes, and he always got the same behavior. There's a tiny negatively charged particle moving through that chamber. He was able to calculate the mass-charge ratio, okay? So he was able to calculate the mass-charge ratio for these particles. And from this, he got the idea that this thing was about 2,000 times smaller than the mass of the hydrogen atom. Now he got a mass-charge ratio. Thomson wasn't able to actually calculate the mass of this particle. And Thomson is accredited with discovering the electron. When he went to publish this, a couple of his colleagues said, "Thomson, there is nothing smaller than a hydrogen atom. Didn't you listen to Dalton? There is nothing inside the atom. It's a hard sphere." And Thomson said, "I don't care what Dalton said. This is what I got for my experiment. This is what I'm going with." He published it. Other people tried the experiment. It worked. The electron was born. So you find a new particle, other people want to learn more about it. And remember, we had a mass-charge ratio, but we didn't have an actual mass, and we didn't have an actual charge. So along comes a scientist by the name of Robert Millikan. Millikan performed what's called the oil drop experiment. Scroll up for me. Okay? Now this is what the oil drop experiment looked like. This is a vacuum tube that this is evacuated in here. And he shot fine droplets of oil, a very fine type of oil in here, through an atomizer, essentially a perfume bottle. Okay? There's a positive plate here, a negative plate here, and there's one tiny little hole in the center, and essentially lets just drops fall down in that line. The other ones get stuck up here on this upper plate. They shoot in ionizing radiation, which, by the way, they didn't have any idea what it was, but it was a cool thing to play with. And what they could do is they could charge this sucker up, okay? And then they could use these plus and minus plates to suspend the oil drop. From this experiment and looking at what the charge had to be to suspend this, and he knew what the average weight of the oil drop was, then Millikan was able to calculate the charge of an electron. Once he calculated the charge of an electron, he was able to use Thomson's mass-charge ratio to calculate the mass of an electron. So Thomson finds the electron. Millikan, through experimentation, was able to determine the charge and then the mass of an electron. And so now we have something very, very tiny that's suspended, that's somehow part of all matter. It's much smaller than the smallest atom known. And it's negatively charged, and we know that atoms are neutral. So this tells us that there are electrons inside the atom. So if there are electrons inside the atom and they're negatively charged, this tells us that there must be something positively charged inside the atom. So what's that positive charged thing inside the atom? What's the internal structure of the atom look like? Well, Thomson's working on this, right? And he proposes what's called the plum pudding theory. Now, we're not British, so we don't understand what plum pudding is, but this is kind of a boiled cake. Okay? So think about making cake batter and suspending some fruit in it, and then putting it in a bowl, sticking it in a pot of boiling water, and cooking it that way. So, plum pudding. Thomson said that the structure of the atom was like a plum pudding. You had this positive glob or spherical amount of positiveness, and it was studded with little negatively charged particles, electrons. So this is what he thought it looked like. I've got this positive mass with these little negative electrons in it. Now, he's going to propose that a friend of his named Rutherford shoot alpha particles at this. Alpha particles had a mass equal to the mass of helium, but it was positively charged. Okay? these alpha particles should just blast straight through an atom if Thomson is right. So scroll up. Okay? To test this model, his friend Ernst Rutherford and his co-workers performed what's called the gold foil experiment. And they're going to shoot alpha particles at a piece of gold foil. I mean, if you sneeze, this gold foil is going to just into nothingness. So he has an alpha source, okay? And there's this detector. In the day that Rutherford was doing this was a big piece of photographic film wrapped around here, okay? He shot his alpha particles through, and they expected them all to go straight through. But that's not what they got. They expected really only to see one spot on their film exposed. But they had some deflections, some spots on either side, some wider deflections, and some that bounced straight back. Rutherford first thought that his student who was doing the experiment screwed up and he made him redo it. Okay, they got the same result again. Rutherford said he thought this was a lot like firing an 8mm shell at a piece of tissue paper and having it bounce back in your lap. Now, so 15-inch shell at a piece of tissue paper and having it bounce back. He knew that the plum pudding model had to be wrong. And let's look at how he explained this shape, this experimental result. Okay, here's what happened. The alpha particles were coming through. Now this kind of blurred out yellow to the edge, that's the atom, okay? That is a nucleus. As the alpha particles were coming through, if they passed through this outer part of the atom, they went straight through. If they came close to the nucleus, which is the concentration of positive charge in the atom, they got deflected some. If an alpha particle was headed straight at the nucleus, it got bounced back. So Rutherford's gold foil experiment gives us what's called the nuclear model of the atom, okay? Which says that almost all of the mass and the positive charge of the atom is concentrated in the core, which we call the nucleus, okay? Most of the volume of the atom is empty space. So now there's a race on to probe this nucleus. Is the nucleus a single particle? Is the nucleus a combination of particles? It's proposed by Rutherford that the nucleus is made up of multiple particles which are positively charged, which he called protons. And the charge of a proton is equal to the equal in magnitude to the charge of an electron. Now, they were able to knock a neutron out, figure out what a neutron was. They can actually create a proton beam. And they figured out that the proton wasn't enough to account for all the mass of the nucleus. So there had to be some other piece in the nucleus. And this last piece is the neutron discovered by Chadwick, one of Rutherford's students, one of his postdocs in his lab. Okay? Now, Rutherford is a very critical individual. He's responsible, or his lab, for 7 Nobel Prizes in chemistry and physics. So this is the real deal, guys. This is the important dude. So now let's look at the atom. Okay? Woo, we've changed a lot from being a solid sphere to an atom being made up of 3 components: protons, neutrons, and electrons. The proton has a relative charge of +1, the neutron 0, electron -1. Okay, I've given you their absolute charges in coulombs. Don't worry about that until you take my physics class. You're not going to have to worry about that. The mass of a proton is 1.00727 AMUs. The mass of a neutron is 1.00866 AMUs. And notice an electron is 0.0055. You can see how much smaller an electron is than a proton. And notice that a neutron has a little bit more mass than a proton. Now, we usually just say proton 1, neutron 1, electron, oh my God, tiny. Okay, and there's what their masses are in kilograms. Don't worry about memorizing those numbers, okay? The proton and neutron are found in the nucleus of the electron, in the nucleus of the atom. The electron is somewhere outside the nucleus. But we don't know where, we don't know what it's doing, okay? And notice when I was talking about mass up here, I talked about AMUs. AMU stands for atomic mass unit, and it's defined as 1/12 the mass of a carbon atom containing 12 protons and, containing 6 protons and 6 neutrons. 6 plus 6 is where I kept getting the 12. So, the minute you learn one thing, it introduces new questions. So, question. If all matter is composed of protons, neutrons, and electrons, how are atoms of one element different from atoms of another element? Okay? The answer is the number of protons in the nucleus. All atoms of the same element have the same number of protons in the nucleus. We call this number the atomic number, and it's given the symbol Z. Let's look at the periodic table for a minute and look at how the elements are ordered. Each element has a unique atomic number, a unique symbol, which is made up of, which contains 1 or 2 letters. The first letter in the symbol is capitalized. Most symbols are based on the English name of the element, some are not. So let's look at this, okay? So let's play. Okay guys, here's periodic table, okay? We start up here with hydrogen. Its atomic number is 1 because it's got 1 proton in its nucleus. You go across the row, there's helium, that's 2. Lithium, beryllium, you see 3 and 4, and they're ordered. Okay? Now, let me draw kind of one of the boxes for you. Gonna go back here. Gonna tilt you guys up a little bit. Okay, if I look at hydrogen, okay, the symbol is here. Sometimes the name is written underneath. Okay, over here, I find its atomic number. Okay, in the periodic table in the front of the room, here we find atomic mass. Notice it's not atomic mass number, it's just atomic mass. Okay, those are the 3 most important pieces of information in the box. All right, now, symbols like the symbol of the elements is going to be the way that chemistry is going to be written. So you need to know some symbols. You need to know the symbols of 1 through 20, atomic number 1 through atomic number 20. You also need to know iron and copper. And I want you to know bromine and iodine. Okay, so that's 24 names and symbols. That's not all 118, just 24. And these are the ones we're going to most commonly use. That's why I want you to know these guys. All right? So, let me break it off right there. And that's where we'll stop on this one, and we'll pick up with isotopes next time.